Okay, let's tackle problem L. They really wanted to make a problem as complicated as possible. But the good news is it will prove to you that no matter how complex the problem looks, you can find an answer if you take things step by step, breaking things down into very tiny steps. Okay, so L. I'm going to rewrite the problem. You know, it starts out f of x, but let's just call f of x y. Why not? Same thing. It's just a number, variable. Y is a variable that depends on x. Okay. And I'm also going to write the right-hand side a little differently. X squared plus 1 plus 4x to the 1/2. And all of that is to the power 1/2. Okay, so I think you can see that that's just an equivalent way of writing it, but more conducive to our techniques. Okay. So our goal is to find dy dx. And we're going to need to make several substitutions, but let's just start with the big picture. The way I look at it is we want to find dy du times du dx. All right. So the first substitute, again, I think it's best to start with the big picture. Well, we have to. It's not a question of the best way. But if we're gonna attack the problem with this approach, then we have to define u as x squared plus 1 plus 4x to the 1/2. That's u. And so y equals u to the 1/2. Well, that's easy. We can certainly find dy du. That simply equals 1/2 u to the negative 1/2. So we've got this factor already. We just have to remember at the end, we have to substitute back in for u using this expression. So we'll get to that. So next challenge, what's du dx? Well, I want to find a simpler expression for u. So we're going to let u equal v plus w, where v equals x squared and w equals 1 plus 4x to the 1/2. Oops, it's hard to write small with this pen. Okay, well, maybe we're getting somewhere. Let's see. We have we have an expression for u, v plus w. So du dx is the same as dv plus dw over dx. That's easy. And that means we're looking for dv dx and dw dx, and we're going to add those two together. So now we've broken the problem yet again into some smaller parts. Well, look, here's an easy one. If v equals x squared, then dv dx equals 2x. So that's the final stage for that term. And let's draw a box around it. Remind us where to look when we want dv dx. So the last part is dw dx. And then putting it all together. All right, so w we said equals 1 plus 4x to the 1/2. Looks like we need to make one more substitution because this is also a composite function. So let's let z equal 1 plus 4x. And look what that's going to do. dz dx, that's just going to be 4, so that's easy. What about dw dz? Well, that equals if z equals 1 plus 4x, then dw dz equals 1/2 times z to the negative 1/2, right? Because what we're saying is w really equals just z to the 1/2. Again, sorry for the cramped handwriting here, but if w equals z to the 1/2, based on our substitution, then dw dz equals 1/2 times z to the negative 1/2. So let's see what we got now. What we want is dw dx. Well, that equals dw dz times dz dx. Well, that equals 1/2 z to the negative 1/2 times 4. Okay, and again, just to check our work, well, yeah, these dz's are going to cancel out, so the multiplication of those two factors will give us dw dx, which we can substitute back in up here. So let's put it all together on the next page. So we said dw dx equals 4 times 1/2 times z to the negative 1/2, so that's 2z to the negative 1/2. Okay, that's dw dx, and we said dv dx equals 2x. Therefore, du dx equals 2 times z to the negative 1/2 plus dv dx, which is the 2x. Okay, so we're getting close now. And dy dx equals dy du times du dx. And we know that's right because these will cancel out. Well, what's du dx? That's right up here. So we're going to bring that down. And what was dy du? Dy du was 1. I'm going back to the previous page here. So dy du, if you look back, you'll see it's 1/2 u to the negative 1/2. And so we're going to have to multiply that times 2z negative 1/2 plus 2x. And that's it. But again, remember, we've defined u in terms of x. We did that earlier. So you can substitute in for that to get back in terms of x's. And we defined z. Let's see, how did we define z? We defined z in terms of x. That was 1 plus 4x. So you can substitute in. And you're going to wind up with a pretty complex expression. But the rest is just simplification if you need to go that far. But just for fun, let's write it out. So dy dx equals 1/2 u to the negative 1/2. Well, that's 1/2, and u we defined earlier as x squared plus 1 plus 4x to the 1/2. That's how we defined it. And so we need to take take the negative 1/2 power of that. Okay. So that's substituting in for u, and we're going to multiply all of that by 2 times z to the negative 1/2, and z we defined as 1 plus 4x times negative, or to the negative 1/2 power. Yeah, 1 plus 4x, and then plus 2x. Let's see if I got that all right. Yeah, I'm checking my notes. I did this on paper earlier, so I'm checking my notes, and this is what it works out to. So we've got dy dx, which is the same as f prime of x, and we've defined it only in terms of just the one variable x. We got rid of all of our interim variables that we use to help solve the problem. So it's just a matter of whether you want to try to find a way to simplify this, but I'm not sure that's appropriate. As one teacher said, in these days, once you have an expression for your derivative, you've done the hard work. You could use a computer now to simplify this, or to graph it, or whatever you wanted to do, where you could find what's dy dx if x equals 101. Well, you could just plug in 101 into a computer, and it would spit out the derivative for that value of x. So I don't know if your teacher insists on try to simplify this expression any further. That's tedious, but it doesn't require any special knowledge beyond just algebra. So there it is. It's a tough problem, but if you break it down into tiny steps, it's doable. You just have to keep track of your tiny steps. That's what you have to. For me, I always like to write down what substitution I'm making exactly. Keep track of the substitutions you're making, keep track of their derivatives, and then it's just a matter of multiplying, for example, different derivatives in such a way that you get to cancel things out. Okay.